So welcome everybody to the ECS Colloquium. Before I introduce today's speaker, Jonathan Bachrach, I just want to mention next week's speaker. That'll be Mark Rabert, who's a former Carnegie Mellon and MIT professor who's the founder of Boston Dynamics, a robotics company. But today, we're very happy to welcome Jonathan Bachrach. Jonathan is an adjunct assistant professor here at Berkeley, where he researches spatial, parallel, and unconventional programming languages, computing, and robotics. Now, before he came to UC Berkeley, he co-founded something called the Other Lab, where he researched programmable matter and geometry workflows for fabrication. And before the Other Lab, he was a research scientist at MIT for 8 years, held postdocs at Stanford and ICSI, and was a researcher in Paris developing new musical platforms. He has studied cognitive science, computer science, the visual arts, and got his PhD from UMass at Amherst. So today he's going to talk about a company called JITX, Just-in-Time Everything. So we'll see how big the scope of that is in a moment. So please welcome Jonathan.
Okay, is this working? Everyone hear me okay? Wow, it's exciting to be here. I think last time I was here, I talked about programmable matter, and a lot has happened since then. Yeah, I guess that was about 6 years ago. So we're starting this company called JITX, and we have an ambitious goal to just dramatically revolutionize the way that people design. I'm going to try to motivate that, give you the setting, the opportunity. I'm going to give some demos, technical details, talk about some of the fun computer science challenges involved, and then wrap up with the potential impact that we're just in time everything. We're starting with circuit board design, and we're going to raise the level of design for that. So let me just give the context. By now, most people have heard of this talk of a new industrial revolution. So the promise is lower cost and more agile production of goods. So there's been talk of third, fourth industrial revolution, but people are sort of saying, well, where is it exactly? The upshot of it, though, is that we can lower the setup costs on manufacturing so we can greatly reduce the production of making single objects, so we can make them much more affordable. So one form of that has caught people's imagination is 3D printers, like this one, the Form 3 that just came out. And so this is like, the idea is that you could have a factory on your desktop, and it has a lot of really attractive properties. One I just want to highlight is that it could potentially make production more ecological in a number of ways. One is that we could, because we can make just what we want, we can make things that we will have a stronger connection to. That will be more meaningful to us, that'll fit us better. And by making something that is more meaningful, we will hold on to it, and that will lead to less waste in general. Furthermore, there's other really nice properties. It's additive, the process of 3D printing, so you waste less material because you're just using the material you need to produce that one object. And because we're doing just-in-time production, we can make just what we need, just in time. Unfortunately, there's a problem with this story, and that's why I say that we haven't seen this real industrial revolution take off. And that is because design is the bottleneck. We can't design as fast as we can now produce. And it's particularly chronic for electromechanical systems. It's excruciating to design even one electrical or mechanical system. And I'll go into that. But the basic problems are that designs require a ton of detail. It's labor intensive. The designs you produce are fragile. hit these dead ends, and there's just not very good reuse. You have to start over each time, more or less. Now, industrial revolutions are a big deal. So, we shouldn't take it lightly. This is the thing that ushers in a lot more productivity for people, so they have more spare time to do what humans really enjoy and maybe are meant to do. And so what I'm going to argue today is that one of the biggest instigators of these revolutions are radically better tools. So great tools allow people to solve more problems with better solutions. And I just highlight here the jacquard punch, which was a big part of one of our industrial revolutions. It was an essential tool of that textile industrial revolution because it made it a lot easier to produce textiles. There were punch cards that instructed the loom how to do the weaving, and that was, hard to do before, and it allowed for a lot more variation in designs. And what I'm saying here is that the impact of that was so huge because it is so highly leveraged. You're really at the top of the food chain here. By making a better tool, a lot more people are empowered by that invention, as opposed to just making one new textile, for example. So now I want to zoom into the topic of today, which is designing embedded systems. So here is an embedded system is by and large, what I want to focus on is the electrical component and the software component that's in the electrical system that is driving some embodied electromechanical system. And let's just say, for example, robotics here. And we have, to drive the robot, we have sensors, we have a processor, and then we have actuators that are driving the mechanical part of the system. So how do we do this today? And so I just want to go through the various steps and show you what's the state of the art of today. So the first step of doing this, sped up 6 times, is to do a rough block diagram. Now how you do that is you pick the parts and you draw a drawing with, everyone knows now how tedious it is to actually draw a diagram. It's never quite right, you're moving stuff around all the time. And then in between actually getting the picture to look right, you have to actually grab the parts and search for them and so forth. So this is just roughing out, this is the first step, roughing out a block diagram to represent the circuit that you want to design. And then from there, you have to actually refine the parts to actually be something that you can actually buy, that they're affordable, they're available, and then that meet the spec, whatever that is. So here we are actually now looking up, making sure that we can get all the parts, and then refining the schematic to incorporate those parts. Maybe having to actually model those parts because they weren't in your library. And then finally, next we go into physical design, where we take the schematic, that represents the symbols. Now we have the packages, which are the physical manifestation. We put those on the board, we lay them out, and then we wire all the components together. So we're now instantiating that schematic in a physical form, but we have to do it so that all the lines don't cross and the wires between don't cross and everything fits. And if it doesn't, which it doesn't all often fit or wire correctly, well then you have to go all the way back and change the schematic and choose parts that make the whole thing fit. So it's not just a linear process. And then finally, not primarily the focus, but just to show what a horror show this all is, you have to set up all your software, which takes forever to run your embedded compilers and whatnot. And then you have to configure it based on the schematic. So that's a picture. And then you have to take the pins that you're driving on the microcontroller and all of that and map it over into the software so that you have your drivers and so forth. So it's super tedious and time consuming. So these are all the steps. It's not just a linear process. There's a lot of back and forth, and it takes a really long time. Okay, so what are the problems? Just to go through them, we've kind of gone through the overall process. The problems are that, first of all, it's incredibly manually intensive. So board layout by itself is all 100% done by hand. There's not really any, you basically have to figure out the wiring and all that. And I'll say that people enjoy that, but it's super time consuming, and it's very error prone, and it can take a huge amount of time. And then from there, the next problem is that you have a lot of conflicting concerns you have to manage through that process. So for example, you have, as you get into more advanced designs, you have signal power integrity, RF, thermal issues, mechanical integration, all those sort of things. And you sort of find those out later, and there's experts that maybe are telling you those constraints, and so you have to manage all these constraints all together. And then if, like for example, a mechanical engineer tells you, well, you need to have this fit in a smaller space. Well, then you have to rip up the whole design and go start all over, potentially, because you need smaller components, or they have to fit in a particular way. And then finally, there's just a lot of back and forth that you have to do. All that communication they're talking about is super time consuming. It's hard to get people to find time to talk to each other and get all this stuff worked out and communicate in some unambiguous way. And so the end result is that this just takes like months for advanced boards. 18 months is what Northrop Grumman tells us for some of their more advanced boards. And there's really no magic to these engineering skills. They're really tried and true, hammered out techniques. So it's tedious and error prone, but it's solvable. So it's perfect for automation. It's not creative work. It's just really complicated, and it's a problem that software should be solving. Okay. So this is bad, but it never stops, right? So like even just the one process, building one board is tough. But the problem is that what if the parts go out of stock, or the volumes change, or customer changes their mind, or the market changes mind? These are all like things that happen all the time, and so you have to go back through that process over and over again. So, and then I just want to highlight just like what a bad set of choices from a client side. You can, okay, I'm going to hire a double E to solve these problems, but you have to justify that by having enough work to like, I'm going to pay a full-time double E. Then you'd have someone who would be on your job and really be fast to service your needs. The other option is to hire a contractor, but that's slow to find the person and then them to have the time for you. And then there's the fact, well, does that person or does the double E you're going to hire actually have all the knowledge you need for the problem? Well, often you need a lot of information, not even just double E, but maybe mechanical information. And all that double E doesn't fit in any one head. And then just finally, I'd just say that it's bad for consultants too. So early on, you're trying to bid for a job and you don't know exactly what the customer wants, because they don't know. Maybe they can't communicate in any unambiguous way to really communicate what they want. So that's kind of a nightmare for consultants, and a lot of times you don't get paid for that work. So this all turns out to be a really great opportunity for automation, and I just want to highlight a few more things that make it nice. One is that unlike other manufacturing tasks, the API, the interface to the factory, is actually pretty well worked out, and it just keeps getting better and better. This is an example of a company, Tempo Automation, which is trying to innovate on pick and place for parts and just give a much better service overall from that API to the actual manufacturing of the boards and assembly of the parts. So that's really good. It's a hard problem, so it's really hard, but it's doable. And furthermore, there's chunks of the space of the problem which you can lop off and really get going and provide a lot of value to people. And finally, there's the big enough market. It's billions of dollars for the design services alone, and electronic manufacturing runs into the trillions. So I'd like to introduce JITX, here to help out. we are just-in-time everything. We're starting with automated circuit board design. And I have myself and Duncan's here. He's my co-founder, and then Patrick was a student here at Berkeley. Both Duncan and Patrick got PhDs here, and I've been adjunct professor. So what I've been working on for the last 7 years since I was talking about programmable matter is actually how to make digital design for chips to be more abstract, get better at the properties of like software, borrow those, and get more productivity in chip design. Duncan was working on this jumping robot. He got a robotics PhD with Ron Fearing, and he was working on robots, and he learned very painfully how bad electronic design is, and beyond that, mechanical design. So he was really excited to make progress there. He really didn't want to design any more robots actually until we made electronic design better, because it's so painful. And I've also been working on geometric workflows and teach a computational design and fabrication class here. Patrick was working on programming language and compiler design, and he also worked with me on Chisel, which is this language we use for chip design here at Berkeley. Okay, so we're funded by Y Combinator and Sequoia Capital. We also got a nice generous gift, a grant from DARPA as part of this Electronics Resurgence Initiative, which is a $1.5 billion program, which is one of the biggest they've ever done. So they really believe in this problem and are throwing a lot of money at it to make it better, not just for circuit board design, but for all electronics, including chip design and so forth. So I just want to go through the approach now. So the idea is, in a nutshell, is that we want to capture the user intent. So what is it people care about? Exactly, no more, no less. What are your requirements? And then from that, we want to have an automated flow that is one click after we've figured out what you want to build, and you've had some dialogue to get feedback that it's really what you want to build. Then in 24 hours you can get a board built and designed, and that's the commitment from DARPA, and we are fully behind that, and we are the performer that's doing the intent-driven design on that. So the number one idea is that we're turning hardware engineering into a computational problem. So, and in order to fuel that, the problem is that today design automation is hampered by a lack of precise medium for communicating with, controlling, coordinating these algorithms. So what I was talking about was that we have these mechanical, electrical, all these different people that are stakeholders and knowledge providers. They are having trouble communicating because they don't have a formal way to specify the information. And moreover, we want to actually automate that. So we want to capture all the information that's important and allows us to actually solve it computationally. And then once we have that representation, we're going to build a compiler around it that goes from this high-level spec, this intent-driven design, all the way down to factory code. And so first I want to just zoom in a little bit on ESIR, which is the electronic system intermediate representation. So that's the way to formally capture all the information. And so here's some of the information that we need. We need, for some, I'll go into this a little bit more, often chips have capabilities that are on pins. We need to know what capabilities are provided on the pins, and then for peripherals, what capabilities do they need to be provided. So that's the provide, requires support. We need all the electrical properties and requirements, and we need to support these smart connections with constraints. So now, once we have all this information, we can provide a lot of automation. So we can solve for pins, we can check and solve for power, and we can automatically perform I/O translation. So the ESIR itself, what I'm showing below is the compiler, going from high level on the left all the way to lowest level, fully concrete, ready to manufacture representation of the board. And it goes through a series of steps. So it starts with the requirements and then goes through all these lowerings that makes it more and more concrete, all these solvers and generators. So I'm going to go through that next. And so what we're doing is we're translating this problem into one where we're treating it like a compiler. And so we can think of the ESIR as the intermediate representation for the compiler. And now we're doing the trick that we did in Chisel, where we are allowing people, we're embedding the circuit design into a programming language. So users can write full generators for entire classes of circuits. We also have this ESIR to communicate the inputs to solvers that can figure out what satisfies all the user constraints. Okay, so that's the basic idea, and in the middle we are showing the solvers and the generators being run by satisfying the high-level constraints and goals on the left, the user requirements. And then by the time we go through all that, we have we've instantiated all the generators, and we've run all the solvers, and then we've now created a fully instantiated circuit that we can manufacture. Okay, so I just want to go very quickly through some related work. As I mentioned, we did figure out a lot of stuff with Chisel beforehand, and so the basic idea there was to embed the rudiments of circuit design, of digital logic design, RTL specifically, into a programming language. And we got really far. So once you do that, you can write these generators, and you can get a lot of reuse. We also pioneered this idea of creating an intermediate representation for hardware in the form of Fertile. And so we created an open compiler for chip making. And that's been highly used, and we learned a lot from that experience. We also did an early version of this called JIT where we didn't do the solvers, the physical design, and we didn't have an intermediate representation. There's been other people, there's been some really great work on doing procedural generation of circuit boards, and also people that are trying to automate it from the visual side of drag and drop interfaces. And those are all good. We're we're raising the level of design even higher beyond that. And then I want to do a shout out to Turning Coders into Makers, which was some follow-on work from people here. That's really nice work that is trying to turn the problem into an SMT problem. And we're sort of working on a complete solution that includes physical design, manufacturing validation, and we're also trying to provide something that has interactive speed. So we do all custom solvers, and but in any event, real nice work. Okay, so let me just go through. Now I'm just going to dive into show you a demo of how this works. So the first setup is the user will put the requirements in the high-level spec, and then we're going to go through the pipeline. And so we do all the chores through to do the component selection, power design, detailed design, pin assignment, place and route, design review. We make sure that it's it's all validated and ready to manufacture by the end, and then at the end we spit out a board. So that's the overall cartoon view of what we're doing. Okay. Now, one nice variation of that, which I kind of alluded to with this idea of a generator, is that we can just work with a particular customer. In this case, it's Hyber, who is providing a satellite modem for IoT. And what they really want to do is sell the service for their satellites. They want to get as many customers as possible. The bottleneck, again, like I was talking about, is the fact that people aren't very good at designing electronics. It's like really slow and tedious, and so they want to just get more and more customers. So they turn to us, and what we can do is provide them with this domain-specific generator, which creates IoT devices by allowing people to choose various peripherals combined with their modem and a microcontroller. And so we can create this combinatorial design process, which will make it dramatically easier for the customers to design boards. Okay. Okay, so let me just go through the demo now. We're going to demo the actual piece at the top, and so we're going to start. We're going to talk about you know, how this all. I'm going to show you the spec and how we go through and what a scenario might be through design. So we'll start with a very small spec, and then it gets, like I said, expanded out into the realistic design automatically. And so what we're going to focus on in this demo is just these star topology designs where we have a processor with connectors and peripherals hanging off of it, and then powering a single power source that powers the whole system. Okay, so we're going to choose from these peripherals. This is very much like what I'm describing, very much what hybrid would want, where you have a bunch of peripherals, and now we're going to also have a bunch of connectors that you can kind of expand out, have inputs from the world and outputs to the world. And so this is our first design. Okay, so we have, in this design, it's a very simple widget where we have a button, an LED, and a connector with power coming in. We've described on this is our input spec on the left, and this is the resulting board. And I just want to say, this is the way we do design here, is that you, on the left, change the spec, and then interactively, you see the result of the board on the right. And so this is very simple starting out, and now first change we can do is say, hey, we actually want a D sub connector. So we can switch that in and we get the result on the right. And then we can add new peripherals. We decide, the customer says, hey, we need accelerometer or EEPROM. We can just add that and get a board, and we see it immediately. And then say we now have user constraints where the button is placed and what the LED are. We can move those and specify them exactly on the board in the coordinate system of the board. And then now for the same board, we can just say, hey, now we need Bluetooth capability. And so we can specify this other processor that specifies that, and we have the full antenna and the Bluetooth on there. Now this is, I'm not showing the change, that's just a command line argument to do that, but the same design will work. It's plug compatible with other processors. Okay, so that same design, actually, if you keep going, works with all these different processors. So depending on, you know, what your constraints are, you could choose any of these, and all of the glue is all done automatically for you. So the same intent just applies to all these different processors. Okay, so now I didn't talk a little bit about the pin assignment problem, but just let me point that out, because this is one of the things that's excruciating when you're doing embedded design, is when you get a microcontroller, it has this pin out that shows all the capabilities on the board. So you have GPIO, UART, I2C, differential pair, SPI, all these features that you care about. So they are all mapped out in this color-coded way. You know, it's kind of representing the matrix. So certain pins have certain capabilities. You don't get all capabilities on all pins. So you have to very carefully map, connect your peripherals that require the capabilities to the pins that serve them, and it's a very tedious process. And so we do that with using a solver. And so the solver will look for all feasible pin assignments and provide you with that. The next problem to deal with that we handle automatically for you is power supply design. And so what we do is, the problem is stated is that you have input coming in from some raw power source, and then you have your loads, which are the peripherals. Now everything's modeled in the system, so it has all the information it needs. So each load has a particular set of requirements: voltage, current, noise, and so forth. And then our solver will just enumerate all feasible designs that match that. And they can all be checked very easily and reliably. But it's a pretty intense process, and we've done a lot of techniques to make it run really, really fast. Okay, so here are some of the regulators that we're using in our power supply. This is just a very simple version of what will be a full-blown system, but just as a demo. And now I'm going to take you through how the system works for that. So we start with where we left off. We have the same board, and so we already had generated power supply. I didn't tell you how it was done, and now I'm going to go through it. And we're going to make a change, so we're going to go from 5 volts to 48 volts. Now in order to handle, so that's the input voltage coming in through the D sub connector. Now in order to handle that, we're gonna need this much bigger regulator. And so that's all done automatically for you. Found one that works. Now say we decide that on the temperature sensor we want to use an ADC interface. That has certain requirements. That requires a particular kind of regulator. It has certain noise requirements, so we have to synthesize a different regulator for that. Okay, so that's the power supply. It's all done automatically, seamlessly. Mostly you don't care. All you want to do is to have it meet your requirements at the highest level. The other problem is processor selection. That's a nightmare. So you essentially, I just want to go through. So if you have a family of processors, normally when you buy a microcontroller, there's a whole family of these microcontrollers. And not only do they have all those pin options, but there's a lot of different pin options, different numbers of pins, different capabilities. And you really have to look through the whole matrix of that and choose the one. And by and large, you want to choose the smallest one, the least expensive one, fewest number of pins that meets your needs. So we automate that as well. So we choose the smallest processor that satisfies your requirements. So let me just give you an example. Here's where we left off. We have this small microcontroller highlighted with the red arrow. Now we're going to add things that require bigger and bigger processors. So we're going to add CAN interface. It'll automatically find the smallest processor from that family that meets the requirement. And then now we're going to add an RGB LED. So two things I'm doing here is I am putting in the need for pulse width modulation to create that RGB LED. And I'm also going to just enlarge it because we need more space because it's a bigger processor. Okay, so that's basically processor selection. I now want to move on to one thing. What is pretty exciting is that now that we have a complete automated flow, hopefully you get the idea that you can change things on the left and immediately see the things on the right. That's a pretty cool way to do design, right? Now you can go even further and say, I don't know how big I want the board to be. Okay, you leave off the size. The system, since it's automated now, can search for the smallest size of the board that'll fit the components that are needed to meet your requirements. And that is because it's automated flow. So it really is not all that much more complicated than just doing a binary search. But the idea is that the whole system is both synthesizing the power supply, choosing the processor, and calculating all these details. It's also doing all the place and route. I should say that all these are fully placed and routed automatically. And it's checking that there are no design rule check violations. So by the time you get to this, this is the smallest board that goes through the entire automated flow, and it's ready to be manufactured. Okay, so now that you have that automated flow, you can go even further. You can say, okay, I've got this family of peripherals. I've got these this power supply. They form these power inputs and loads. The system will do all this automatic stuff, choose a processor, find the power supply, optimize place and route, DRC, all that. But now we have this input spec. We can actually fuzz that input spec and really look through the whole space. So this is one example of an automatically generated input spec, just like kind of a generative grammar for inputs. We could drive the system. And then we can run that. Why not just find the smallest board as well? So we ran that through, and this is just a sampling of them, 13 boards. These are all fully placed, routed, verified, ready for manufacturing. One thing I'll just note is that we're sort of applying a really good idea from software testing to the hardware domain, because now we've turned hardware design into a software problem, and so we can apply these good ideas. I just want to note that we're able to achieve densities that are on the high 90s, high 80s, and low 90s, which is actually quite competitive with humans in place and route, which is really nice. I just want to also point out how the idea of actually finding the smallest board is amazing, because it's such a time saver. Because often you're just happy if you get one board to work. But imagine if you can, our system, I should also say, our system will find a place and route given any polygon as an output. So that's some of the really hardest things, and that's the stuff where you pull your hair out over, because you've already got a design and now you want to change the shape, or you want to find the smallest version. You make a change, you can always find the smallest board, no matter what the components are. If you change your requirements, it flows through, it's automated. Okay, the other thing this whole system creates is the opportunity for even higher level design. We can even get in people that don't know anything about electrical design. All they want to do, they really like LEDs, and they want to create, they know art. So they can actually draw these pictures, they can paint where they want the LEDs. And so this is a very high level, this is kind of a demo of an idea that we've been working on, which is where we have inputs from SVG, which is the vector format you can produce from Illustrator. So users can actually draw out where they want the LEDs and draw the artwork they want on the board and the outline and all that. And the system will translate that graphical input into these fully operational boards here. So this makes it a lot more accessible for people to make electronics. Okay, now I'm going to switch gears and just kind of dive down on one technical area that we are pretty committed and excited about. So this approach is really only as powerful as the programming language it's embedded in. And I just want to make one aside that I think PL research is one of the most important areas of research because of its impact on software design productivity. And at JITX, PL is our killer tool. So we use this language called Stanza, which is especially good at embedded domain-specific languages. So it was designed from lessons learned with Chisel and Fertile. We even did a mock version of Chisel just to try out the system. So it's easy to learn. It's got a static type system. It's a sophisticated macro system. In fact, the whole grammar of the language is all written in the macro system. So it's a fully programmable list file macros, but with an infix surface syntax. It's got a Python-esque syntax. Okay, so that's just kind of the overall high-level version of it. We learned a lot in doing Chisel about IRs for hardware. And I just want to point out one thing. So we make ESIR a macro. Okay, so that means it's a syntax that we've extended the language and provided this new language for electronic systems. Unlike the way we did Fertile, we actually make ESIR executable. And so what's nice is, so if you just have static ESIR describing a circuit, it will just self-evaluate. So it will produce new ESIR that's exactly the same. But you can actually you can add any amount of program to it to make it more and more powerful to create a generator. So that's a really powerful way to do it. So it's a seamless transition from a literal to a procedural description of the circuit. So let me just show you a quick thing. Here's the self-evaluate, super simple circuit here with an accelerometer and a processor, and we connected them up. And on the left side is the input, on the right is the output, self-evaluating, right? Now, what we do is we can put some Stanza code right in the middle of the IR, and that thing will now wire together the processor, and it'll connect all the pins of the processor to, except for pin 8 to out. So this is kind of arbitrary code here. Or this is an example of how on the left you can write the loop. What that does is it eventually executes and then produces all those connections on the right. So when you run it, it produces the ESIR on the right. So we still have this static ESIR, but it's running a generator which is creating the circuit. Even more powerfully, we can write recursive functions. Here's just creating an adder tree, and on the left we have a recursive function. So again, we're embedding within this static ESIR this code snippet that powerfully describes the connection in a highly parametric way to construct this circuit. And on the right is after running that. So this makes it much more accessible for people to get started. They can start with static ESIR and then slowly add constructs to make their circuit designs more and more powerful. And eventually you're describing a generator, and you can make something that is highly parametric. It's parametric in the sense of code being writing functions and having parameters in code. Okay, the other aspect that we draw on, it's pretty critical, is that we want to describe visual things with code. So we believe very strongly in writing code, and the reason is that visual programming uses direct manipulation. Now that is the obvious thing to do when you're describing visual things, but the downside, and often people call this WYSIWYG. So that is what you see is what you get. The problem with WYSIWYG is what you see is only what you get. And so it's very hard to add abstraction and get reuse and create these generators with a WYSIWYG system. Not that it's not impossible, but we know how to write this. And how do you get the best of both worlds? Well, the idea is have this dual view where interactively you can make the changes on the left and get the circuit on the right. Now, Stanza has a very interesting read eval print loop, so it's the interactive thing. So it actually allows you to it implements the full language. It allows you to do live coding, reloading. It's based on a virtual machine, and unlike it does full type checking, so you get feedback on your system, full language implemented. So you can really, once you have developed your generator, you can actually run it in a working system. And so it's the full code that you're developing out, but you get interactive speeds to develop it. So that's a really important part of how we're doing it, and it's a pretty nice achievement, especially for a statically typed language. So I just want to, we're developing something that's got a lot of really hard problems. I just want to point out some of the interesting computational problems and get you excited about that. Some of the things that we're up to. So one of the challenges, if you didn't realize, is just that physical design is really hard. Okay, so this is a t-shirt making fun of the auto router. So auto routers are really, really hard to do if you can't change the placement as well. So if you're given some fixed placement, some fixed pin assignment, and then you got to do auto routing, well, maybe that's impossible. Who knows? And so people don't use auto routers. It's unfair to auto routers. There's rarely any auto placers. And the point is that you have to do all these things all together. You have to do pin assignment, placement, routing, and potentially even simulation in the loop to actually get a good physical design. And so we are innovating in that space. We currently now do pin assignment and placement together, and we're working on combining all the concerns. We're working with some very cool data structures and optimization algorithms. It's a very hard problem, but we're making really good progress, and you've seen some of the early results. Okay, the other thing that we're doing under the hood is we're doing massive design space exploration and system optimization. So we have a lot of these high-level requirements. They all have to be satisfied. But it's not enough just to get one solution that satisfies it. we want to search through that. We want to optimize. Maybe later say, hey, we want the minimum size, minimum cost, all that. So we want to actually enumerate them efficiently and sample that space. The other thing we want to do is we want to communicate powerfully to the user and say, is this what you meant to design? So we want to sample that design space and really get feedback early on so the user actually learns what they really want to build. And that'll speed up design quite a bit. And so we really need this whole system to work at interactive rates. So we have to work very hard on how to fail fast and how to optimize everything and all the custom solvers, all kinds of tricks in optimization and enumeration of very large spaces. Okay, and then the other thing too is that if you have an input spec, how do you debug it? How do you communicate that back to the user effectively? Just as like a compiler will communicate back a type error. How do you do that? Here's a little example of a design, and these are the user just kind of like threw on various things, and actually very quickly you want to know, well, hey, that's too expensive. I don't really want to build that. Then you want to have this conversation with the system. How do you communicate to the user effectively? So it's a really interesting problem. How do you find inconsistencies in the design? And how do you get that back? You need to know that as soon as possible. And then we are scaling out our system to model 5 million components. We have to have a vast library. How do we automate automate that? Because it's a lot of components. We think that we can write generators for a lot of the packages and so forth and get a lot of advantages there. But eventually we have to sort of figure out how to scrape the data sheets. And then moreover, the problem keeps being a problem because we have to have manufacturers actually abide by the specs. And so how do we ensure that? How do we push this out into the world? So that's a really interesting problem. We've got buy-in early on from TI, and we're really excited, and they're excited about what we're doing. So we're feeling it's a good direction. And then how do we automate the testing? So like the reason we can get volume production, why we have to go to volume production is like actually the testing is really expensive, and that takes a lot of engineering. How do we also automate the testing so that we can make it feasible to do bespoke design? Okay, so today we demonstrated a system with low-speed digital designs. We're actively building out a design capable of handling designs with even more complexity. Eventually, we're JITX. We're really trying to push for the full electromechanical design, and this is where design is excruciating. So what's the impact here? Well, the basic idea, I try to argue that design is really the bottleneck. We want to turn engineering into an elastic medium. We capture all the EE knowledge in computational form. We want to go beyond agile. Agile is kind of like doing the first design quickly. We want to make it interactive to explore lots of designs. And then we want to capture the formal spec and actually have that, and that'll be good documentation and allow us to have a good start on next designs. So we're raising the level of design, and we hope to democratize design, allow more people to participate because it's easier to design. We'll have more designs made. There'll be more solutions. People get more what they want. There'll be more designers, more entrepreneurs out there. We also want to do eventually better than human designs. We feel that we're very confident that we can achieve that for just the reason that we can explore more of the design space and bring to bear massive amounts of EE expertise. I'd just like to thank Richard Lin and David Biancaline, who worked on the earlier JIT PCB work and contributed a lot to that. We're funded by Combinator and Sequoia and DARPA, and we'd like to thank them for believing in us and our collaborators, Northrop Grumman and HP. I'd like to now end with a request for you to join the revolution. Build a tool. It's really the thing that has the most impact in my mind, because people will use it and you'll amplify your efforts. Invent a new programming language. It's really important that we have a lot more programming language research. If you're interested, take my class in computational design fabrication. And finally, I'd like to say that we're hiring. We're looking for algorithmics people. Email me if you're interested. Thank you very much. I'll take any questions.
So thank you very much. It wouldn't be Berkeley if you weren't invited to join the revolution. So, so do we have any questions for the speaker?
It's a wonderful vision. First, a very low-level talk. What is the algorithms that you run under the hood? Specifically, say, for the layout of finding the optimal small PC board, what's going on there? Are these like standard IC layout packages using simulated annealing, or how do you optimize that stuff?
Yeah, right now we are using simulated annealing. We have, it was the most modular thing that we could use to incorporate all the constraints. We also, some of the things we had to deal with was like that some of the constraints might be relative placement of components. So there's a lot of stuff that had to be managed all through that. We also, like I said, some of our moves are actually doing pin assignments. And so while we're doing placement of components, we're looking at better pin assignments that make it feasible to bring things together.
You showed us those 13 or so little PC board examples. I mean, how were they compared? How were they actually laid out? How much did the user have to do, and how much was completely automated under the hood?
That was completely automated, yeah. So I just talked about a little bit, if you got complete automation on any given some board, it'll either fail or work. And since I'm going through the whole flow, through place and route, all the way through checking it, you can actually just keep shrinking the board until it works. So you just do the best computer science algorithm on that, and efficiently search that space. So that's effectively what we're doing. More of the magic and the hard work was in the placement algorithm, which took a long time. And currently, like I said, we're moving into dealing with some of the other concerns in placement. Because it's like, if you want to get as good as humans and get it to more aggressive designs, then you have to worry about how routable is the placement.
Now, a very high-level question.
Yeah.
You said that we start with high-level specifications. Just how high-level can that be? If I come in and says, I want to make a jumping robot, should not be more than a pound and should jump at least 3 feet high, is that high enough? Can you compile from there on down, or where is that input level?
Well, I was trying to give some examples. Like we have categories of components. So there are features that you want. So you want to sense temperature. So you don't necessarily say how you want to do it. And I was trying to give the idea that you can start to specify even more when you care about the properties of that sensor. But in terms of like an overall engineering, we're not at the level of actually saying jumping robot. But we're more on the lines of like, you've got the basic block diagram architecture. The back of the envelope is kind of what we're after.
Any more questions?
Hi, so I see you had like ADCs and some other stuff built in. So I'm just wondering, like, how much detail do you have on the analog end? Are you accounting for bandwidth, noise, whatever? How do you deal with that? Because you say it's for digital design, but you have some analog stuff there.
Duncan?
Yeah, so we're primarily digital. We have some basic
Pass the mic over.
Sure. Yeah, so we're primarily digital, but mostly we have some basic analog functionality. Nothing too intense. So imagine you can have analog circuits to the point where it doesn't matter where you put the components or route the traces.
Okay. but do you have like specs listed for your analog blocks? Like, let's say, like, can I put like in your ADC command, can I list I want one with this bandwidth, this sampling rate, this noise?
Yeah, we haven't built that yet. It is planned out. And like everything else, we fold it into the ESIR and then throw it to probably a specific constraint solver or a generator for synthesizing analog signal chains.
Okay. So, because in that case, like, you'll have, I think it'll be very tough there, because a lot of like the analog stuff, a lot of like the noise data, for example, is just in a random plot in the data sheet. Hard to extract.
Yeah, you might find that's the case for all components, is that the real data is in the charts and the front page is like marketing information. Yeah, not just for analog.
I would just say, though, like one more comment is that we definitely have to acknowledge that as we move to more analog designs, we're going to have to do simulation in the loop as well. There's no way to get around that.
I have one question.
Okay.
Do you think it'll be possible someday to add a constraint? I want the market to be at least $1 billion. So
That would be nice.
very high level constraints, yes.
Yeah.
Maybe, okay. So if there are no more questions, let's thank the speaker again.
Yeah. All right, thank you. Thank you.